Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. This second video lecture is the continuation of my previous first video lecture of week 16. In first video lecture, we have already learned about eigenvalues and eigenvectors for a square matrix. And now in this video lecture, we are going to discuss again the problem eigenvalues and eigenvectors by using some mathematical problems for practice. Suppose we have a 3 by 3 matrix. In the first video lecture, we have find the eigenvalues and eigenvector for the 2 by 2 matrix. And now in this video lecture, we are going to find the eigenvalues and eigenvectors for 3 by 3 matrix. You see over here, this is a 3 by 3 matrix. Now the matrix A minus lambda I3 is obtained by subtracting lambda from the diagonal elements of A. This means that first of all multiplied lambda with the identity matrix 1 0 0 0 1 0 and 0 0 1. This is the identity matrix of order 3. So multiplied the identity matrix, multiplied the eigenvalue lambda with the identity matrix, you will obtain at the diagonal of the identity matrix lambda, lambda and lambda. So just only subtract the lambda from the diagonal matrix, from the diagonal of the matrix A. You see over here 5 minus lambda 4 2 4 5 minus lambda 2 2 2 and 2 minus lambda. Now the characteristic polynomial of A is a determinant of A minus lambda I3. Using row operation to simplify the determinant, we obtain lambda A minus lambda I3, which is equal to 5 minus lambda 4 2 4 5 minus lambda 2 2 2 2 minus lambda. And now subtract second row from the first row, we obtain 1 minus lambda minus 1 plus lambda 0 4 5 minus lambda 2 2 2 2 minus lambda. Now expanding this polynomial, expanding this determinant by with respect to the first row, we obtain 1 minus lambda into 5 minus lambda into 2 minus lambda minus 4 minus into minus 1 plus lambda into 8 minus 4 lambda minus 4, and after simplification we obtain 1 minus lambda into lambda minus 10 into lambda minus 1. Now after simplification we obtain minus into lambda minus 10 into lambda minus 1 whole square. So we know solving the characteristic equation of matrix A, minus into lambda minus 10 into lambda minus 1 whole square is equal to 0. The characteristic equation is A minus lambda I into x, but when we take the determinant of A minus lambda I, this is actually the characteristic equation. Determinant of A minus lambda I is the characteristic equation, and now the characteristic equation is equal to minus into lambda minus 10 into lambda minus 1 whole square is equal to 0. Solving this equation, we obtain two eigenvalues, lambda is equal to 10 and lambda is equal to 1. Now to find the eigenvalues of the matrix A corresponding to the eigenvalue 10 and 1. The corresponding eigenvectors are found by using three values of lambda in the equation. A minus lambda I3 and to x is equal to 0. Why we say that in this equation the eigenvalues are three values? Because lambda minus 1 whole square is repeated, lambda minus 1 into lambda minus 1 is equal to 0. So we have three eigenvalues, lambda is equal to 10, lambda is equal to 1 and lambda is equal to 1. Now this is actually from this equation, in this equation we put matrix A, put the value of lambda, suppose 10 or 1, and multiplied with the identity matrix, and then subtract this matrix from the matrix A and then multiplied with the vector x, we obtain a homogeneous system. And then taking the augmented matrix like you see over here for lambda is equal to 10, we obtain A minus lambda I3 into x. So multiplied 10 with the identity matrix and then subtract from the matrix A, we obtain minus 5 4 2 4 minus 5 2 2 2 and minus 8, and this is the eigenvector x1 x2 and x3 is equal to 0. The solution to this system of equation are x1 is equal to 2r, x2 is equal to 2r, and x3 is equal to r, where r is a scalar. Thus, the eigenspace of lambda is equal to 10 is the non-dimensional space of vectors of the form r into 2, 2, and 1. Dear students, uh, convert this augmented matrix into row reduce echelon form. You will get uh, the last row will be 0, so x3 will be free variable. So suppose x3 is equal to r, where r is a real scalar number. So putting r x3 is equal to r and the second equation, you will obtain x2 is equal to 2r, and then substitute the value of x2 and x3 in the first equation. You will obtain the x1 value is equal to also 2r. Thus the eigenspace for lambda is equal to 10 is a non-dimensional space of vectors of the form r into 2, 2, and 1. So first of all, convert this augmented matrix into row reduce echelon form. You can get easily or simply you can convert this matrix into echelon form. You can get easily the value of x1, x2, and x3, and this is actually the non-trivial solution. X is equal to 0 is the trivial solution, but we need the non-trivial solution because the eigenvector is a non-zero vector. Now for lambda is equal to 1, putting lambda is equal to 1 in this equation, a minus lambda I3 into x is equal to 0, we get you see over here lambda value is 1, so 4, 4, 2, 4, 4, 2, and 2, 2, 1, and this is the eigenvector x1, x2, and x3. The solution to this system of equation can be shown to be x1 is equal to minus s minus t, x2 is equal to s, and x3 is equal to 2t. How we can get this solution? Dear students, I have already told you that convert the augmented matrix into echelon form or convert the augmented matrix into reduced echelon form. If we convert the augmented matrix into reduced echelon form, we can easily find these non-trivial solution. X1 is equal to minus s minus t, x2 is equal to s, and x3 is equal to 2t, where s and t are scalars. Thus, the eigenspace of lambda is equal to 1 is the space of vectors of the form minus s minus t, s, and 2t. Separating the parameters s and t, we can write minus s minus t, s, and 2t is equal to, taking common s, we obtain minus 1, 1, and 0, and plus t, we obtain minus 1, 0, and 2. If we multiplied s with this matrix and multiplied t with this matrix and then adding, we obtain minus s minus t, s, and 2t. Thus the eigenspace of lambda is equal to 1 is a two-dimensional subspace of the R2 with the bases minus 1, 1, 1. This is actually the first eigenvector, minus 1, 0, 0. This is actually the second eigenvector. So if an eigenvalue occurs as a k times repeated root of the characteristic equation, we say that it is of the multiplicity k. Thus, lambda is equal to 10 has multiplicity 1, while lambda is equal to 1 has multiplicity 2. And this example, because in this example, lambda repeated 2 times. Lambda is equal to 1 and lambda is equal to 1. Now, another example you see over here, to find the eigenvalues and corresponding eigenvectors for this matrix 1, 2, minus 1, 1, 0, 1, 4, minus 4, 5. The characteristic polynomial is lambda cube minus 6 lambda square plus 11 lambda minus 6, and its vectors are lambda minus 1 into lambda minus 2 into lambda minus 3. So the eigenvalues are 1, 2, and 3. And the corresponding eigenvectors are x1 minus 1, 1, 2, x2 minus 2, 1, 4, x3 minus 1, 1, and 4. Dear students, this is actually the home task for you. First of all, use the characteristics equation. Determine a minus lambda I3 is equal to 0. You will obtain a characteristic equation in which lambda will be obtained, and solve this characteristic equation. You can easily find the value of lambda, and then using the equation a minus lambda I into x is equal to 0, putting the value of lambda in the equation, putting the value of lambda is equal to 2 in the equation, and putting the value of lambda 3 in the equation, you will obtain these three eigenvectors. X1 is the eigenvector corresponding to 1, x2 is the eigenvector corresponding to the eigenvalue 2, and x3 is the eigenvector corresponding to the eigenvalue 3. Now you can easily verify. You see over here, I want to tell you about the eigenvalues using the characteristic equation. Determine a minus lambda I is equal to 0. So this is matrix A, multiplied lambda with the identity matrix, and then subtract this matrix with from this matrix. We obtain 1 minus lambda, 2 minus 1, 1 minus lambda, 1, 4 minus 4, 5 minus lambda. Now expanding this determinant with respect to third column, minus 1 into 1 minus lambda, 4 minus 4, minus 1, 1 minus lambda, 2, 4 minus 2, plus 5 minus lambda, determinant 1 minus lambda, 2, 1 minus lambda is equal to 0. And now after simplifications we obtain minus 1 into minus 4 plus 4 lambda, minus 1 into minus 4 lambda, minus 12, plus 5 minus lambda into lambda square minus lambda minus 2 is equal to 0. And now taking common minus 4 from this equation, we obtain minus 4 into lambda minus 1, 4 common from this factor, minus 4 into lambda minus 3, taking common 4 from this factor, 4 into lambda minus 3, and 5 minus lambda. Now factorize this polynomial, lambda minus 2 into lambda plus 1 is equal to 0. Now minus 4 into 2 lambda minus 4 plus 5 minus lambda into lambda minus 2 into lambda plus 1 is equal to 0. Now minus 8, taking common 2 from this factor, minus 8 into lambda minus 2 plus lambda minus 2, multiplied these two factors, 5 minus lambda and lambda plus 1, we obtain minus lambda square plus 4 lambda plus 5 is equal to 0. Now taking common lambda minus 2, after simplifications we obtain lambda minus 2 into minus lambda square plus 4 lambda minus 3 is equal to 0. Now taking common minus from this factor, minus lambda minus 2 into lambda minus 3 into lambda minus 1 is equal to 0. So we have three eigenvalues like you see over here, lambda is equal to 2, lambda is equal to 3, and lambda is equal to 1. So the final characteristic equation of the polynomial, minus into lambda minus 2, lambda minus 3, lambda minus 1, and we can write minus lambda plus 2, lambda minus 3, lambda minus 1 is equal to 0. So the characteristic equation you see over here, minus lambda square plus 5 lambda minus 6 into lambda minus 1, and now we can write minus lambda cube plus 6 lambda square minus 11 lambda plus 6 is equal to 0. Why we multiplied these three factors you see over here? Why we multiplied these three factors? From these three factors we can easily find the lambda value 2, 3 and 1. But if we need the characteristic equation, then simplify the equation, you can find the characteristic equation. But in this case you have already the eigenvalues 1, 2 and 3. Now you see over here, after verifications we obtain the lambda value 2, 3 and 1, and this is actually the characteristic equation. Using this characteristic equation you can easily find the lambda values 1, 2 and 3. Now using the eigenvalue lambda is equal to 1, find the eigenvectors. Using lambda is equal to 2, find the eigenvectors. Using lambda is equal to 3, find the eigenvectors. For the eigenvector you can use the equation like you see over here in the previous slide. You can use the equation of this equation, a minus lambda I into x is equal to 0, putting the value of lambda, a minus lambda I is equal to x is equal to 0, putting the value of lambda and multiplied the value of lambda with the identity, you obtain a matrix. Then subtract the matrix from the matrix A, you obtain the final matrix, and multiplied the matrix with the matrix X, you will obtain a homogeneous system. And then taking the augmented matrix and convert the augmented matrix into row reduce echelon form, you can find the solution x1, x2 and x3, and this is actually the eigenvectors corresponding to the eigenvalue. So dear students, the conclusion of this video lecture and the previous first video lecture of week 16 is that actually we have a matrix, a square matrix. For the square matrix, we need to find the eigenvalues and the eigenvectors. For the eigenvalue lambda, use the characteristics equation determinant a minus lambda I. You see over here, this is actually the characteristics equation a minus lambda I, determinant of a minus lambda I is equal to 0. From this you will obtain a characteristics equation, you will obtain a polynomial, and that polynomial lambda will be a pair, and then solve the polynomial, solve the characteristics equation by using factorization. You can find the eigenvalue, and then put the eigenvalue in this equation a minus lambda I into x. Use the identity matrix according to the order of the given matrix A. If the order of the given matrix A is 2, you can use the identity matrix of order 2. If the order of the matrix A is 3, you can use the identity matrix of order 3. So multiply the lambda value with the identity matrix, you will obtain a matrix, and then subtract the matrix from the matrix A, you will obtain a single matrix, and then multiply that matrix with the matrix X, you will obtain a homogeneous equation like you see over here. If we write this equation, we will obtain a homogeneous system, and then this homogeneous system actually has two solutions. One is the trivial solution, and another is the non-trivial solution. X is equal to 0 is the trivial solution, but x is equal to 0, we cannot consider x is equal to 0 because eigenvector will be non-zero. So we need to find the non-zero solution for the homogeneous system. So for the non-homogeneous, for the non-trivial solution, convert this matrix into row reduce echelon form. Then you can easily find the solution of the matrix, like solution of the system, like you see over here, x3 is equal to r, x1 is equal to 2r, and x2 is equal to 2r. Then write this in the column matrix, like you see over here, 2r, 2r and r. So taking common r, 2, 2 and 1 is the eigenvector corresponding to the eigenvalues. And now this is the end of this segment. Thank you. Allah Hafiz.